Hello student, and welcome to the course Urban Rail Transit Tracks, Stations and Yards. In the previous lesson, we explored the fundamental working principle of turnouts. By the collaborative efforts of various components within the turnout, trains can smoothly transition to their required directions. It's worth noting that the turnout we examined in the last lesson is just one of many types. This time, we'll dive into various kinds of turnouts. In spite of many different types of turnouts, it's possible to distinguish turnouts in terms of their basic form. We have standard turnout, curved turnout, wide turnout, and three-way turnout. We also have diamond crossing on the railway intersection tracks, which doesn't change the direction of moving trains. Standard turnout or single turnout is most important in all types of turnouts. In standard or single turnouts, a distinction is made between right-hand and left-hand turnouts depending on the direction the diverging track takes, seen against the direction of the switch point. Single turnouts generally have no superelevation. If the radius of the diverging line ends in front of the crossing, it is referred to as a turnout with a straight crossing, otherwise it is called curved turnouts. Curved turnouts can be divided with regard to the direction in the diverging line into outer curved turnouts and inner curved turnouts. In a curve, the turnout can diverge in or against the direction of the curve with the straight track laying in the curve and the turnout track curved opposite through the track or in the same direction. If the deviating line goes in the direction of the middle point of the track curve of the main line, it is called an inner curved turnout. Conversely, when it diverges in the opposite direction, it is referred to as an outer curved turnout. In other words, in an inner curved turnout, the center point of the track curve of the main line and that of the diverging line lie on the same side, and for the outer curved turnout, they lie on a different sides. In spite of the position of curved turnouts in a curve, an angle of the turnout and the length of the tangents do not change. The inclination of the original form remains the same. The necessary changes in the length of the rail is done by adjustment of the closure rail. The entire turnout is rotated around the middle point of the turnout, also known as the point of the intersection of the tangents. In general, either the curve with a larger load or with a larger radius is designated as a main line. The crossing of the curved turnouts can lie in the turnout outer rail of the main line. In combination with the prevalent partially uncompensated accelerations, the check rails and the wheels of the vehicle are subjected to the heavy loading. Curved turnouts cause particularly high maintenance costs and should, if possible, be avoided. In outer curved turnouts, which are placed in a curve with superelevation, it is inevitable that there will be negative camber in one rail. This must be taken into account when specifying the speed through the turnout. Symmetrical outer curved turnouts are the type whose branching rail and the main rail have the same but opposite curvature. A symmetric turnout or Y switch or Y points has trailing ends which diverge symmetrically and in opposite directions. The name originates from the similarity of their shape to that of the letter Y. Y switches are usually used where speed is at a premium. In North America, this is also called an equilateral switch or equilateral turnout. Common switches are more often associated with mainline speeds, whereas Y switches are generally low-speed yard switches. One advantage of a symmetrical turnout is that they can have a coarser frog angle using the same radius of the curvature than a common switch. This means that they give rise to a less severe speed restriction than the divergent branch of the common switch, without having to resort to more expensive switches with a moving frog. For this reason, they are sometimes used on a main line where it splits into two equally important branches or at the ends of the single-track section in an otherwise double-track line. A three-way turnout is used to split the railroad track into three divergent paths rather than the more usual two. There are two types of three-way turnouts. In a symmetrical three-way turnout, its left or right branches diverge at the same place. In an asymmetrical three-way turnout, the branches diverge in a staggered way. Both types of three-way switches require three frogs. The complexity of the symmetrical switches usually result in speed restrictions. Therefore, three-way switches are most often used in stations or depots, where space is restricted and low speeds are normal. Symmetrical switches were used quite often on Swiss narrow-gauge railways. Asymmetrical three-way switches are more common because they do not have speed restrictions compared to standard switches. However, because of their high maintenance cost due to special parts as well as asymmetrical wear, both types of three-way switches are replaced in two standard switches whenever possible. In areas with very low speeds, like depots and on railroads that had to be built very cheaply, like London Railroad, three-way switches were sometimes built as stop switches. If a mating of two tracks on the same level cannot be avoided and a change between the tracks is not desired, then crossing elements should be created. A diamond crossing is a specialized railroad track configuration designed in that case to allow two separate tracks to cross over each other while maintaining the track continuity. It is called the diamond because when viewed from the above, the overlapping tracks form a shape resembling a diamond. Diamond crossings are often used in areas where two railway lines intersect, enabling trains to cross from one track to another while avoiding collisions with trains on the intersecting line. This configuration is particularly useful in rail junctions, crossovers, and intersections, facilitating the smooth and safe flow of train traffic. Diamond crossings can be complex and require careful design and maintenance to ensure the safety and efficiency of railway operations. This enables the intersection of the several tracks without changing direction. In the context of the crossings, four rails meet, which places special challenges on the track guiding. Simple crossings, as are already known from the turnout, guarantee safe well-set guidance in an acute-angled section. A double crossing with bank-held check rails is arranged in the area of the obtuse-angled meeting of the two lines of rails. A diamond crossing is considered normal if the angle of the intersection is equal to that of the single turnout, and the intersecting tracks are straight as well. Crossings can also be curved in similar way to turnouts in order to be able to use them in curves. The same criteria applied in this process as when turnouts are customized to the curvature of a curve. The crossing is curved at the intersection center point while maintaining the main dimension. Both rails have the same radius after bending. The change of the length is compensated by the harmonization of the closure rails. In conclusion, each type of turnout serves specific purposes and caters to the unique requirements of the rail networks. Standard turnouts are most common and straightforward, allowing trains to switch between straight tracks. Curved turnouts, on the other hand, facilitate the transitions onto curved tracks, providing flexibility in train routing. Symmetrical turnouts are used to split the single track into two, enabling trains to take one of two routes. Three-way turnouts, as the name suggests, offer three possible directions for train movement. Diamond crossings are specialized railway track configuration that allows two tracks to cross over each other while maintaining continuity. Alright, that's all of this lesson. See you next time.